Hi, my name is Brian Caffo, and this is the regression Coursera class. And today we're going to talk about count outcomes and Poisson GLMs. These slides were originally Jeff Leek's from his data analysis Coursera class. The class is co-taught by Jeff and Roger. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so the key idea here is that many data take the form of counts, and that we can't necessarily model counts in the same way that we model other things with linear regression or binary regression, the two topics we've covered so far. So some examples of counts are calls to a call center, number of flu cases in an area, number of cars that cross a bridge, and so on. I work in biostatistics, so we deal a lot with counts that are of the form number of cases of a certain sort. So this, for example, these kind of Poisson models are highly used in infectious disease epidemiology for modeling counts of disease outbreaks. The data may also be in the form of rates. In fact, I find it difficult to think about Poisson data without thinking about it in terms of some rate or some monitoring time. So what we mean by rates then is a count is a count per unit time. So for example, the classic variable that follows the Poisson model is radioactive decay. So this is counts of radiation detection hits on a detector. That count is, of course, dependent on how long you're running the detector, right? So it's not relevant to talk about the count without talking about how long you monitored things. So it's count per unit time. And I would also say that the raw percentages can be modeled as count data, they're obviously counts, but the percents, which kind of seem like binomial processes, can be modeled with Poisson models, especially when the probability is very low and the sample size is very large. That's a classic case where we simply model that data as if it were Poisson, even if there is no bound on or even if there is a hard bound on the number of possible successes. So, and we're going to talk about a lot of these different things today. Linear regression with transformation is an option, and we'll go over logging the outcome just because it's an important special case. So the Poisson distribution is a particularly useful distribution for modeling counts or rates. Here I'm defining a rate as a count per some monitoring time. So some examples of the Poisson distribution: so web traffic hits, incidence rates in epidemiology, binomial type processes with small p and large n. And there's a huge use of Poisson models for analyzing contingency table data. We won't cover that, but people do that. So the use of so when I say a contingency table, you have let's say, I don't know, something like hair color. Let's say a person is blonde or not blonde, and eye color. A person is blue-eyed and not blue-eyed, let's say. And if you were to sample a bunch of people and just tabulate the counts of these things, that would be a so-called contingency table. At any rate, the contingency tables are often, I would say, mostly analyzed with log linear models, Poisson log linear models. So hopefully everyone's had the inference class or is taking the inference class at the same time. But if not, let me just give you a couple of quick things about the Poisson mass function. So we say a random variable x is Poisson t lambda if the probability that x takes on a specific value is t lambda to the x e to the negative t lambda over x factorial for x account starting at 0 and going to infinity. Often, in many cases t equals 1, so you might specify this in terms of lambda. So the mean of the Poisson random variable is expected value of x equal to t lambda. And so also, so of course that means the expected value of x over t is lambda. And then the variance is equal to the mean. That's an interesting fact about the Poisson. And then the Poisson tends to a normal as t lambda gets large, which means if you fix lambda, then this means as t gets large. So if t is some sort of monitoring time, right, then that t is the very natural thing to get large. Lambda, by the way, you can see right here, lambda, by the way, right, is interpreted as expected counts per unit time. So lambda has units. That's a nice thing. It's a units per time. All right, let's see. Let's look at the Poisson distribution for a couple of different values. So here I'm just plotting a Poisson with a lambda of 2, and in all these cases t equals 1. So here I'm plotting a lambda of 10, and here I'm plotting a lambda of 100. I have to use a different horizontal axis scale because lambda of 100, right, the mean is 100, the variance is 100. That shifts the distribution substantially along the x-axis. So notice there's a different scale. You can see, kind of what it looks like here, what it looks like here, and then also you can tell that it looks almost exactly like a Gaussian by the time you get up to lambda equal to 100. So we don't, I don't want to go through the math. In the other class we go through the math. In boot camp 2, I think, in my other class I go through the math. But here I'm sort of showing that the mean and the variances are equal numerically at least. So I'm going to take x out to infinity. So for the purposes of this example, infinity is, what is that, 10,000? 10,000. But this goes pretty fast, so you could do 100,000 if you wanted to. And you plug in whatever lambda value you want, and then our mean is just the sum of the x values times the mass function values, right? And my sigma squared is just the sum of the squared deviations around the mu value times our mass function values. So here's my mu and my sigma, and of course it's 3, exactly equal to the lambda we used for plugged in as the theoretical value. Okay, and then you can, if you know the expansion for E, then you can actually prove this rigorously, but maybe not necessary for this class. All right, so let's investigate Jeff Leek's website, because Jeff Leek's website is blowing up. So consider the daily counts to his website. Here's his website. You can all go to it and increase his number of hits. So in every instance, the unit of time is always 1 day. So we're just setting t equal to 1, right, as 1 day. So the Poisson mean is interpreted as web hits per day. If we had set, just to give you how this works, right? If we had set t equal to 24, then and the measurements were in the per day, right? Then the lambda that we would get out of the model will be interpreted as web hits per hour. And okay, so it's that. I hope everyone sees that. That's easy. And we'll go through an example later on of how you actually incorporate, let's say, one, and it's very easy if everything was measured for the same amount of time, but let's imagine if one count was measured in a day, and then the next one was measured in a half of a day, and the next one was measured in a day, and the next one was measured in a half a day, or something like that. I don't know why that would happen, but let's say someone, for, I don't know, whatever, there was a mess up in the program, and every other day it only recorded half a day's web traffic. We'll show you later on in the lecture how to have a varying t value for every observation in your regression model, your Poisson regression model. So here it is. You can get it. I think Jeff put it on Dropbox. the Julian dates are these, they're a count in a number of days from a specific date. The nice thing about R is when it prints it out, though, it prints it out in a nice formatting, as we can see. And so here's the outcomes. It looks like he's not getting very many visits. He's not getting very many visits on these days, but you can see, let's just double check, right? We can see that the measurement is every day, and then here's the exact, I'm sorry, here's the Julian dates. I guess I'm wrong. R doesn't automatically print the Julian dates out as dates. So here's the original date variable in the date time format, and here's it converted to Julian dates. So you can see that they just increase by 1 each time, right? So because Julian dates are a measure of the date from a specific date in days. Okay. So here's a plot. Looks like, you know, looks like Jeff is blowing up. So we could model this as linear regression. So, and we've talked a lot about linear regression, so let's just go through how we would do that just as a refresher at this point. And because you guys are all linear regression ninjas at this point, this would be no problem for you whatsoever. So you could model the number of web hits as having an intercept and a slope times the day, and then you could add an error term, right? Just a standard linear regression. You know the interpretation for all this at this point. Oh, and Jeff gives the Julian day 0 there. Let's see. So here's the plot of the fit, and that looks good. And we'll talk in a minute about why you might want to model this instead as Poisson. But before I do that, I want to talk about an aside. Maybe one of the reasons you might want to model it as Poisson is because you want to talk about relative increases or decreases in web traffic, right? You want the coefficients to have relative meaning rather than absolute change meaning. And that would be that's nice, right? That's something something seems pretty reasonable about doing that. And I just wanted to mention that one idea you might think of is to just take the natural log of the outcomes. So that would just be exactly this model, that the log of the web hits is a line. And this is not the Poisson model, right? The Poisson model is going to model we've talked about GLMs, it's going to log the mean of the y's, the conceptual mean of the y's, not the observed mean. So that actually avoids some trouble. So logging the outcomes has a problem, as we saw that the first couple of days the number of web hits was 0, and so you can't take log of 0. So that's a problem. But it also has a very different interpretation. So if you just log your outcome and you're happy with interpreting on the log scale, then log, so number of web hits is still the number of web hits. Julian date is the Julian day. B0 is the log number of hits on day 0. B1 is the increase in the log number of hits per unit day, and E is the variation, epsilon is the variation. Or Jeff wrote it as E here. But what's interesting about logging outcomes is it's a very special transformation in that it imparts kind of a particular interpretation of the coefficients when you exponentiate them. So I'm going to define this guy, and maybe it's a little small, so let me just write it out bigger. E to the expected value of log y, where y is any random variable. It has to be positive. Kind of only makes sense to do this for positive random variables. Is the so-called geometric mean of y. And you might have heard of the geometric mean and say that does not look like what I've heard of. But I'm thinking of this as the sort of population geometric mean. If you just had a bunch of data, if you just have y1 to yn, and you wanted to estimate that, then you would just estimate this expected value with the average. Let me write it out a little bit bigger. So we would clearly just e to the 1 over n summation I equals 1 to n log yi. Clearly, if we wanted to estimate that guy, we would just plug in that for that expected value that we don't know. It turns out that this is equal to just the product I equal 1 to n yi raised to the 1 over n power. And at any rate, the geometric mean is, this is what probably most people have heard of as the geometric mean. But that's an estimator, and what's its estimand? Well, that guy is its estimand, right? That's what it's estimating. If you collect an infinite amount of data, it converges to that. The geometric mean is the natural model for anytime you want to model something that's a relative quantity. So if your data is a bunch of percent increases or decreases, then clearly the natural definition of the average is some sort of multiplicative average, not some sort of arithmetic average, the standard average. And because when we think of these percent increases or decreases, we multiply them, right? If you have your data point is 1.03, representing a 3% increase in whatever, then that number intrinsically has a multiplicative interpretation. And so the geometric mean is extremely useful for that. So anyway, here's my point. When you take the natural log of outcomes and fit a regression model, your exponentiated coefficients estimate things about geometric means rather than about the natural scale means, okay? So in this case, in our exact example, e to the beta naught is the estimated geometric mean hits on day 0, and e to the beta 1 is the estimated relative increase or decrease in the geometric mean hits per day. And if we had other covariates, we would have to add the phrase holding all the other covariates constant. There's a problem with logging the outcome if you have 0 counts, and in fact, this is a problem in this particular data set. The thing that people often do is they just add a little constant. So instead of modeling visits, it's visit plus 1 or plus 0.5 or something like that. The problem with that, of course, is that the interpretation is no longer it's not the estimated relative increase or decrease in geometric mean hits per day, it's the estimated relative increase or decrease in geometric mean hits plus 1 per day. And so it messes up the interpretation a little bit, but for the time being, let's forget about that and just interpret this as if we didn't add the plus 1. Okay? So when we do this model with the logged outcomes, and I'm printing out the exponentiated coefficients to 5 decimal places, and so we get 0.002, 1.002. So that's representing a 0.2% increase in web hits per day. Okay? And that's nice, right? Because it's a relative interpretation, which is kind of what we want. We want to talk about our web hits increasing as percents rather than talking about the raw number of web hits we get per day. And it's especially useful, if your traffic is really exploding, right? And it's more meaningful to talk on the log scale than on the natural scale. Okay, so that's logging. Logging in the mathematical sense, not like with an axe. Okay, let's compare linear and Poisson regression, and I'll also add some thoughts about logging versus logging the outcomes versus a model with the log mean. Okay, so linear just models this guy, that the number of hits is has a linear relationship, and that implies an expected value relationship between the outcome and the linear predictor. The Poisson log linear model models the log of the expected value as the linear predictor. Okay, let me do that again right here. Okay, or you can invert that statement and get that the expected value is the exponent of the right-hand side. Okay, now notice from this equation how we might interpret beta 1, right? So we might say expected value of number of hits for a Julian date equals, let me just say j plus 1, so minus expected value of number of hits given the Julian date equals j, right, that works out to be b1, right? And so raising that e to the b1 then is the relative increase in the the relative increase in the mean number of hits per 1 day increase. And then if we add other covariates, it would be the relative increase per day, holding the other covariates constant. I just want to add on the slide, it's not on the slide, but just because I added a little text on it earlier, then there's the other option of modeling the log counts, right? And how is that different from modeling that? And that is a model on expected value of the log of the number of hits, right? Which differs from what the Poisson model is accounting for, right? This guy, because expected value and log can't switch, this guy logging the outcome is a model on that, whereas this guy is a model of the log of the expected value. So the Poisson model, the coefficients are going to be naturally interpreted in terms of the expected values of the outcomes. The geometric mean is going to be kind of naturally interpreted the expected values on the log scale. So anyway, that's the difference between logging your outcomes and fitting a model where the linear predictor is on the log of the mean. Okay. So just to reiterate, right? So the expected value of that is that guy, right? Expected value of the number of hits is that guy if we exponentiate both sides of our log linear model. And then we can, of course, pull out the E of beta naught, and then Jeff is just reiterating that if the Julian date is increased by 1 unit, then the expected value is multiplied by e to the beta 1. So e to the beta 1 is the relative increase or decrease in web hit, in expected web traffic per 1 day increase. Poisson regression in R is very easy. You just fit GLM. You just want to make sure the family equals Poisson. The log link function is the default link function. And you can just add the plot with an AB line statement. I'm sorry, AB line, that's for the linear model. And then lines, Jeff grabbed the actual X and fitted Y values and then colored that in blue. Okay, so the GLM fit is in blue and the linear model fit is in red. Okay, and notice the GLM fit is of course nonlinear, right? Because it's linear on the log of the mean scale, so so that's why it's a little curved there. But you can see the fit is pretty similar. Okay, so there is some concern over the mean-variance relationship in this data set. So here you can define a generalized form of residual. These make more sense the larger the actual means are. So it's kind of hard if you were to, for example, in a GLM do binary regression. The residuals always look kind of funny, but as whatever process you're studying, if it looks more Gaussian, like in the Poisson case, if you have larger counts, then the residuals look okay. They can kind of be interpreted like regular residuals. And so in this case, we would think that we would want variation increasing with the mean, but that doesn't appear to happen. So a common to me, it's kind of looking a little like that. And if and I think just to highlight this, let's go back here. We kind of with the Poisson, you expect variation to be increasing with the mean. It doesn't appear to be really happening in this data set. A very common way to account for some amount of model misspecification, even though you feel like you've got the mean model correct in statistics is to use these so-called robust standard errors. One thing you can do in this case is you could always try the instead of family equals Poisson in the model, you could do family equals quasi-Poisson, and then it will add a multiplicative factor, so the variance is not just equal to the mean, but it's the mean times a factor. That may or may not be the, it's not 100% clear that would work in this case, but a general thing that you can do is in statistics is to get kind of these so-called robust standard errors, and Jeff found this answer to this question in Stack Overflow, where you can use these so-called sandwich variance estimates and get a confidence interval that uses these so-called model agnostic standard errors. The process by which this works is basically it tries to get a very general estimate of the variance that isn't highly dependent on the model, with the exception that maybe the mean relationship is specified correctly, and then it forms your confidence interval, and it uses asymptotics to uses the assumption of large sample sizes to get a confidence interval that's robust to model misspecification. Your model doesn't have to be Poisson. What you really need is you need to make sure you got the mean model correct, and you need large sample sizes, and then these will give you kind of robust standard errors. This is the basis for a lot of different techniques in statistics. Okay, and so here we plot we give the confidence intervals for the computed in the normal way versus the confidence intervals computed using these robust standard errors, and you can see the lower limit is a little bit lower than the lower limit calculated normally, and the upper limit is a little bit larger than the upper limit calculated in the normal way, and so it robustifies the standard errors. It makes the intervals a little bit wider. Also remember, these are very small numbers, so if we can do our quick exponentiation and say, we're throughout we're kind of estimating about a 0.2% increase in web traffic per day. Okay, let's talk about modeling rates. So what if you wanted to look, I made a mistake earlier, the simply statistics column is just the count of the web visits that are purely from simply statistics, okay? So imagine if I wanted to model the percentage of total web hits that were from the percentage of total web hits that are from simply statistics. So I wanted to kind of condition on the total number of web hits, and I wanted to model the percentage that were from simply statistics. So this is the expression that I'm interested in. I can log both those sides. I can log both sides, right? And I want it to be a log linear model. And then I can move this log number of web hits on the other side. So what's the result? The result is that we have we model our log count, so the count of the number of hits from simply statistics, and we put in the log total number of hits as a term without a coefficient, so-called offset. If you have some sort of monitoring time or anything like that, you put that in as a log offset, and then your interpretation of your Poisson mean is then the Poisson mean relative to this quantity. Okay, so if you put in time, if we had simply put in log 24, then all of our previous results would have been in the terms of the intercept, for example, will be interpreted in terms of number of hits per hour rather than number of hits per day, assuming a Poisson model about the way in which hits accrue at the site. So in this case, the outcome will be interpreted as expected number of log of the expected number of hits. Well, let me say, let's go back to this guy. E to the beta naught, for example, will be the expected number of hits originating from simply statistic out of total number of hits at day 0, okay? So here it's pretty easy to fit. You can put the offset, you can put it in as a comma offset, or you can actually put it in the model itself. You can actually, you know, add plus off. You can actually add a plus. You can actually add a plus, and then that variable, if you wanted to, would give you the same result. Either way, since it doesn't matter, let's leave it like it is. Also, you know, Jeff says data equals G data, so you don't really need that guy and that guy right there, okay? And so now we can model the count of the hits to his website originating from the Simply Statistics website, the other website that he writes. Okay, and here he's plotting the fitted means in blue, but these are the fitted means originating from Simply Statistics, and here in red is the overall count. The original, see, this is, I'm sorry, so if you didn't notice, that was GLM1 for the red one. Okay. Oh, and I should have pointed out, you know, because the visits, again, because the visits have zeros in them, he's modeling not relative to visits, but relative to visits number, not relative to total visits, but relative to total visits plus 1. Here's the rates, so not the count, but the rates. And what you can see is this, you know, so the rate of hits from Simply Statistics was basically 0 for a while, and then it went up, and the model, you know, fits it as not exactly 0, but close to 0, and then shoots up. So that's our rate model, and that is now that's plotting the fitted values minus the assumed rate at that point. Well, in this case, the fitted value divided by the number of visits plus 1 in this case. So yeah, there we go. And here is the fitted values divided by the number of visits plus 1. Okay, so that's how you model rates in R. So it's just a function, or in Poisson models, it's just a function of adding an offset being a term that does not have a coefficient, and you want your offset to be the log of whatever you want to be in the denominator of your rate equation, and then the Poisson model will R will just kind of take care of the rest. So don't forget to log it, right? That's one thing. Don't forget that 0 and negative values are going to cause a problem for you, and otherwise, this is an incredibly useful thing, this modeling rates using Poisson models. Okay, so some more information. Jeff gives some links on log linears and multi-weight tables. That's a whole discipline in and of itself. Maybe not the most relevant for data science concentration, but for things like biostatistics, it's a very important topic. Wikipedia has a nice article on Poisson regression and a nice discussion of so-called overdispersion. This tutorial, and then there's this problem occasionally that you have the 0 count is sort of more than, the Poisson model would kind of expect would look something like that, right? And in the 0 count has this extra amount in it that the Poisson model wouldn't anticipate. And you might think in this case this might happen, right? That you have a lot of more 0 counts maybe early on than you would expect, or something like that. And this is called zero inflation. Zero inflation. And there's a fun set of models called zip models. Zero inflated Poisson models that you can use. And there's a lot of different ways to to account for zero inflation. There's a lot. I like zip models, I think, just because I like the word zip. But this is a problem that frequently occurs with count data, and so it's something to be aware of.